All right, so here's another one. A tow truck is dragging a box containing Baby Yoda, consider him part of the box, at a constant speed. The friction on the wheels of the tow truck propel it forward along the ground, okay? So the first thing that you should notice in this picture is the words constant speed, okay? And then that lets you know that the forces are balanced, okay? Because it's moving at a constant speed. Okay, so let's make an interaction diagram. Okay, so we have the tow truck, okay, and the box. And again, remember, we're using these letters, okay? Ground, we're using instead of floor this time with a G, and of course the earth, okay? All right, so let's see what's happening. Okay, so it will assume the tow truck is moving this way because that's the way that it looks like it's going, okay? And tow trucks pull things. All right, so the tow truck is going to pull the box. So that's going to have a tension. Okay. And then the tow truck is on the ground. Okay, so anything that has a surface is going to get a normal. And since there's motion between the truck and the ground, we know there's also going to be a friction. Okay. Same thing with the box, right? If the box is touching the ground, that's going to be a compression normal. And since the box is sliding on the ground, that's going to be a friction. All right. So anytime there's anything resting on the surface, there's going to be normal. And if there's relative motion between them, then you know you're going to have to add the friction. Okay. And then everybody's going to get a gravity, even the ground if you want, but who cares? And the box. Okay. All right. So let's take a look at the box. All right, so I'm going to look and see how many interactions the box is having, okay, and I can see that there are 4. All right, so I'm going to start with box as the feeler, okay, and I'm always going to start with the force of gravity on the box from the earth, all right, because that's just an easy one to start with. Okay, I'm going to start with gravity, and I always want to end with friction, okay, because friction is the most complicated one, so it's best to add that one last, okay? All right, and the forces are balanced, and especially up and down, for sure we know they're balanced because there's not even any motion up and down, okay? So the ground, force normal, box ground is going to push up, okay, equal to the weight, okay? So those two are going to balance, okay? And then how does the box feel the tow truck? Okay, the box feels like it's getting pulled to the right, okay, because it is getting pulled to the right. So force, tension, box, tow truck. Okay, so I know that the tension force on the box is pulling the box to the right. Okay, and since I know the forces are balanced, my only choice left is going to be friction. And that's going to act opposite the motion, right? Because if not, if there was no friction, this tension force, right, would make this box speed up, right? Because like hitting with the bowling ball, okay? So this is going to be force, friction, box, ground, okay? And those are going to be equal, okay? And they all 4 don't have to be equal, right? Oops, let me not do that. Okay, you know, like for example, this one, right, like these could be smaller. Okay, as long as those 2 are equal and up and down is equal. Okay, but they all 4 don't have to be equal. So however you want to draw it. I mean, it doesn't really matter. Okay, all right, let's look at the tow truck now. 1, 2, 3. And I can see the tow truck is also having 4. So tow truck's my feeler. I'm going to add the force of gravity first. Force, gravity, tow truck, earth. Okay, same thing with this one. It's going to have a normal force from the ground. Force, normal, tow truck, ground. Okay, remember force, type, feeler, dealer. Okay, now this is where it gets a little tricky. Okay, this one is sort of helpful because it tells us the friction propels it forward. Okay, but sometimes you don't really know that. So what we want to do is we want to think about this tension force. Okay, so the tow truck is pulling the box to the right, but then in turn with that, the box is pulling the tow truck to the left. Okay, that's going to be your Newton's third law pair. Okay, so even though I think we would think of the tow truck as the one doing the pulling, the box, remember, is also doing the pulling, equal and opposite. Okay, it's just, we don't think of it that way. We think, oh yeah, the tow truck is pulling the box. Like we don't look at that and say, oh, look at that box pulling the tow truck. We don't say that. Okay, but it is also doing it. Okay, so that force is going to be to the left, force, tension, tow truck, box. Okay, and then in order for this to be able to move at a constant speed, there has to be some rightward facing force. Okay, and the only thing that could be is the friction. Okay, so remember when there is tires, tow truck, ground. Okay, when there is tires, right, you want to think of that friction sometimes like a traction, right? Like your wheels catching on ice or catching on snow is difficult. That's why it's hard to drive on snow. Okay, on a regular road, right? Like if you have good tires that are like grippy, not when they're all worn out, right? Good grippy tires on the road, those can get a little bit of traction, right? And that traction is kind of what propels that car forward. Okay, so again, friction is the tricky one, so think about doing it last. Okay, all right, and then I'm going to look for the Newton's third law pair, all right? And since I can see B and T are my objects, I'm looking for the feeler dealer that have the B and T. Okay, and I can see it right there. Let me make this another color. So that one and that one are going to be my Newton's third law pair. Okay, equal and opposite. Same size. These purple ones look a little long, but same size and opposite direction.